Hello, this is lecture 10, the last lecture in chapter 2. It's about matching using the Smith chart, and in particular we are talking here about the stub matching problem. So we discussed matching earlier in the chapter, and basically it was needed to improve the signal delivery as well as the power delivery to the load. The process of making the source sees a matching impedance, so it will put out its maximum power possible, at the same time minimize reflection so we can improve the signal quality that arrives to the load. We presented a few possible approaches to matching, and this particular section here in the chapter is about the stub matching. The concept of the stub matching is to find a location on the line at which the presented impedance of the load is matched to the real part. Both real parts are matched to each other at this point, and all what we need is to simply match the reactive part by adding a reactance. So we are finding a location on the line at which the real part is matched to the real part of the other side of the transmission line, which in this case here the source. And if the real part matches the real part, then we can match the imaginary part to the imaginary part by adding or subtracting a reactance. We can do this in so many possible configurations. This configuration here is basically we're adding a stub in series. So actually, as the real part is matched to the real part, we add a reactance here. However, we can do it also in susceptance. If the real part matches the real part of the admittances, then we can add a shunt susceptance here in parallel, which takes care of the imaginary part. How do we get the reactance in this case, or the susceptance in that case? Basically through the use of another transmission line. We know a transmission line, if shorted at the end, it presents a reactive component at the input side. So in this case here, the input component will be connected in series, so we're worried about the reactance. In this case here, with connected in parallel, so we worry about the susceptance. As it turned out, there are two other configurations here, which are shown below here, and they are identical to those except for one thing, that the stub here now, or the stub there now, has an open circuit end instead of the short circuit. As it turned out, that open circuit presents again a reactive input impedance here, and open circuit here will represent a reactive input susceptance there. So these two configurations here can be used as well for impedance matching issues. So as you can see, there are four configurations here that we can choose from. However, as it turned out, that each one of these actually have two possible solutions, because you look at this plus or minus, right? That means you can possibly add a reactance or subtract a reactance. So you may be able to find a place on the line where the needed reactance is inductive, another place on the line where the needed reactance is capacitive, and likewise for each one of those other configurations. So reality is that we have 8 possible solutions here. As you can see, there are 8 columns in this table here. All right, there is a series stub or a shunt stub, and for each one of those is either capacitive or inductive, and that could work out for the short circuit stub or the open circuit stub. You have 8 possible combinations. So I'm going to work out with you 2 of those and leave the rest for you to figure out, because they are not that difficult, they are quite similar. So the example that we're going to work out together here is a short circuit stub. All right, here's a short circuit stub. And we're going to work with a shunt configuration, so it's connected in shunt. And we'll be able to find the capacitive or inductive. That means the other location here, for example, where it would be capacitive and the other location would be inductive. So let's first look at this analytically. The process is, here's your load. You want to find locations on the line where the real part is equal to the real part of the source. And I'm talking here admittances because we are working in shunt. So we want to talk about the real part of the admittance of the load at other locations is equal to the real part of the admittance of the source. So as I work out my equation here, I'm going to come up with this kind of a result. And this kind of a result here is telling me that 2 possible polarities here for B shunt. That means I can come up with 2 different answers for DMS. DMS is the location for the stub on the line itself. There's DMS. How far am I from the load end? And I can see that there will be 2 answers here for DMS. One here, maybe another there. I'm showing only one on the diagram. At the location of interest, that admittance should equal an opposite to the admittance of the line itself to compensate for it and give you a zero total admittance at the source end, because the source is pure real. And this is the equation right here, which is telling us that we are using the stub to tune out the admittance of the line at that location. So the admittance of the stub with the admittance of the line cancel each other, and from there on I can see only real impedance or real admittance. So these are the equations to do it analytically. So now let's see how we can do it on the Smith chart. We realize that we have two transmission line problems. The main transmission line, where Z sub L needs to be moved until we find that the real part is matched to the real part of the source. And then the second transmission line problem is the stub moving from the short circuit until we match the admittance of the transmission line. These are two transmission line problems. That means two Smith charts. We can do them both on the same chart if we are careful. We're going to do here two separate charts, as you will see. So let's start with the first transmission line problem. Again, we start by choosing a normalization impedance, and that could very well be the characteristic impedance of the source, for example, R sub S, and that's actually what we chose here. So we divide Z sub L by the characteristic impedance that we chose. So here's point 1 now, where we normalize the impedance of the load to the characteristic impedance or the reference impedance that we chose, and then we need to get that in terms of admittance, because you remember we are working a shunt stub problem, so we need the admittance. So we go opposite to the other point, mirror image across the origin on a constant gamma circle, rotate 180 degrees, you get the admittance right there. So if this was Z sub L, this is Y sub L, normalized obviously. So we got Y sub L. Now we need to move towards the generator, and we need to find the place where the real part is equal to 1. So we have to identify the circle where R is equal to 1 or G is equal to 1 in this case. Here's the real part is equal to 1, that circle. So I move here and I find that I can have either this solution where the real part is equal to 1, or if I continue moving I have this location here where G is equal to 1 again. Either of these 2 points is good for matching, because we already matched the real part. All what we need is add a susceptance to match the imaginary part. So what do I need to do is read the susceptance at these locations. So the susceptance of this location here is read on the B circle, and the susceptance for this location here is read on this B circle. And as you can see, they are located symmetrical with respect to the horizontal line here. That means one of them is going to be positive and the other one is going to be negative. So the line susceptance here is positive. That means we negative that to get the stub susceptance. And the line susceptance here is negative. That means the stub susceptance needed for that would be positive to compensate for that. So we take the readings of susceptances right here and right there, and we record those. And we'll move on to find out the stub required to cancel that susceptance. And that will be the second transmission line problem. And here's a chart for that. These are the two susceptances here. This is one susceptance value, and here's the other susceptance value. So if we call this one here solution number 1, 0.3, and this one here solution number 2, which is 0.4, the stub susceptance for solution number 1 is going to be on the other side, and the stub susceptance for this one is going to be on this side, because like we said, the susceptance of the line at this point here is positive, so we need a negative susceptance here to compensate for it. Susceptance of the line here is negative, so we need a positive susceptance to compensate for it. So I'm starting with a short circuit stub. That means the admittance is infinity, and I move from the stub short circuit until I find the length of the stub that gives me that susceptance, and that's one solution, and go all around to get the length of the stub that gives me the other solution. And these are the two values for the two lengths. Here's one and here's the other one. Those lengths again that we are going to get from the chart are normalized lengths, which can be translated back into physical lengths by denormalizing with respect to the wavelength of the problem. So that concludes lecture number 10 of chapter 2 and actually concludes chapter 2 as well. And I'll be seeing you in future chapters. Thank you.